Okay. Hello, everyone. My name is Siddharth Maharana. I am a PhD student at IUCAA Pune, and I'm presenting this uh, talk on behalf of the PASIPHAE team. Before I begin, I want to thank the organizers for this opportunity to present our work. Uh, Before diving into details of the talk, I just want to give a brief overview of what I'm trying to cover in this talk. Firstly, I plan to give a brief overview of the PASIPHAE survey and how that drives the goals of the Wallop instruments, and then give glimpses of the optical optomechanical design of the instruments, as well as polarization, modeling, and calibration. And then I will conclude with the current status of the instruments. So PASIPHAE is an acronym for Polar Area Stellar Imaging in Polarization High Accuracy Experiment. Just keep it. Yeah. And the key features of the surveys are that we want to cover around 4,000 square degrees or more of the galactic polar sky in both the northern and the southern hemispheres. And we want to measure polarization, in particular linear polarization, with systematic uncertainty of 0.1% in HDSS-R filter. And covering this much area, we will be able to measure polarization of about 1 million stars. Currently, similar measurements are there in the galactic plane using the GPIPS catalog, but in the polar regions, the sampling of stars is very low. And we are aiming to go up to 16 magnitude depth in our band. More details of this survey and its scientific and technical goals can be found in the PASIPHAE white paper by Tasis et al. And the main motivation for carrying out the PASIPHAE survey is to create this three-dimensional magnetic field and dust cloud tomography map of the ISM using stellar polarimetry and stellar distances as the two tools. Currently, we have a large stellar distance catalog from the Gaia mission, and what is really missing is this large sky stellar polarimetry map. And a demonstration of how to carry out this tomography has been presented by Gina in her paper in 2019. So anybody interested can look into that paper. And the PASIPHAE survey is trying to create this map using two dedicated polarimeters called Wallop. And Wallop is an acronym for Wide Area Linear Optical Polarimeter. And again, to give an idea of why we want to create this three-dimensional tomography map, I think a lot of this has already been covered yesterday, so I won't spend much time into it, but just briefly saying that this can be used to create better foreground models for CMB mode polarization search, as well as probing unanswered questions about the physics of dust and magnetic fields in the interstellar medium and other science cases. And coming to Wallop instruments, there are two Wallop instruments that are currently under development, and we are planning to build install one of these instruments on the 1 meter telescope in SAO, South Africa. This is called Wallop South, and another one on the 1.3 meter telescope on Skinnakis Observatory, Greece, called Wallop North. This is the same observatory where RoboPool is currently installed. And both these Wallops are currently under development at IUCAA in Pune. Wallop South is the first among the Wallops scheduled for commissioning in 2021. And for the remainder of this presentation, I will give the results as well as the details of Wallop South instrument. That is because Wallop North and Wallop South are very similar between themselves. So presenting the results of one would give everyone the idea of how the other one is. And before I dive into the design itself, just wanted to share with everyone about the collaboration. So it's a collaboration between 5 institutes spread over 4 continents. IUCAA in India is involved in the instrument design, photometry pipeline, and instrument calibration. University of Crete in Greece is involved in instrument control softwares. the data reduction pipeline, and Caltech is involved in the 3D tomography pipeline. SO in South Africa is involved in the telescope operations, and University of Oslo is involved in the CMB foreground maps using this stellar polarimetry data. And this project is funded by ERC, National Science Foundation, Infosys Foundation in India, Stavros Niarchos Foundation, and the NRF in South Africa. And the whole PASIPHAE team consists of various professors, engineers, and a large team of grad students and postdoc. And I've just put up mugshots of everyone so that you get an idea of who our team is. Actually, most of the members are giving talks in the conference, so you will get to know them very well. Okay, now coming to Wallop instrument details, design goals. As you would guess from the requirements of the PASIPHAE survey, broadly the requirement for Wallop would be, it should be wide field, and it should have high polarimetric sensitivity and accuracy, and that is because we are looking at the galactic polar regions where the polarization is really low. So we need to have high accuracy and high efficiency. And by efficiency, I mean time efficiency, so that we can carry out observations much faster. The table here captures the technical goals of the Wallop instruments. We are aiming for a polarimetric sensitivity of 0.05%. And one of the key features of this instrument is this 4-channel one-shot polarimetry, and the total number of cameras being 4. I'll talk about this in a succeeding slide to make it more clear. The field of view goal is 30 by 30 arc minutes, and the aim for the optical design is to achieve seeing limited PSF, close to seeing limited PSF for the entire field of view. So what is 4-camera one-shot polarimetry? So the top-level idea of what Wallop instrument would do is captured in this figure on the left. So if we give any input field to the Wallop instrument, we want to get as output 4 images of the full field on 4 different cameras. And these 4 images correspond to 0, 45, 90, and 135-degree polarizations. And carrying out differential photometry on these would give us the Stokes parameters Q and U. To contrast this with conventional polarimeters, the image on the right is of RoboPol, where all the 4 channels are imaged on the same detector. So as you can see, each star corresponds to 4 spots, and from those we find the Stokes parameters. Now, doing polarimetry with the Wallop-like system with 4 cameras has 3 major advantages. And these are, because sky is an extended object, if all the 4 spots are imaged on the same detector, the background basically doesn't get subtracted, and it's high. By having each channel image on different detectors, the background is reduced by a factor of 4. For crowded fields, there is no intermixing of images as seen in, for example, in this RoboPol field image. And also, point 3 being, for some science cases, which it may be very beneficial in the sense that it will enable extended object polarimetry for a very large field of view of 30 by 30 arc minutes, which has not been possible till now. Now I will dive into the details of the Wallop instrument design. Firstly, I will talk about the Wallop South's optical model, and the overall optical design of the Wallop South instrument is part of a publication whose reference I have mentioned here. If you want more details of the design, you can refer there. I will just give quick overview of the overall optical system of Wallop South instrument. So the table here captures the telescope and the sight conditions for Wallop South instrument. The 2 key parameters are the sight seeing, which is 1.5 arc second. That is a median seeing at SAO, and the temperatures can go from -10 to +40 degrees Celsius. And the Wallop South instrument design, including the optical design, has been made to operate optimally for these sight conditions. Uh, Before we began the design of the instrument itself, there were few guidelines or few guidelines that we wanted to follow. One was we had to limit the length of the instrument to 1 meter from the telescope focal plane because of the uh, size of the available space. I mean, available space at the bottom of the telescope. We wanted to maximize the throughput of the instrument uh, for better efficiency of observations. There no mirror should be in the pre-polarizer optics so that there's no introduction of polarization crosstalk because of these optics. And once the polarizer system separates the four channels, we did not want any leakage between the four channels that would corrupt the measurements of the Stokes parameters. And one major problem that we face is correcting for the dispersion by Wallerstein prisms. I have a slide on this, and I'll talk about it a little later as well. But briefly, carrying out this four-channel, four-camera polarimetry for a wide field needs large split-angle Wallerstein prisms, and the split angle of Wallerstein prism depends on wavelength, so that introduces a spectra in the outgoing beams. Okay, so this slide is basically to show the overall optical model of the Wallop South instrument. The image on the right here captures the overall main instrument model. The instrument begins from this point marked 1, which is the telescope focal plane. From there, a set of optics called the collimator assembly creates a pupil for the entire field, which is then fed to a system of optics. We call that polarizer assembly. And the polarizer assembly carries out two main tasks, which is it splits the incoming beam for the whole field into the four channels, 0, 90, 45, and 135 degrees. Additionally, it steers these four channels into four directions. Here, the four channels go into plus minus X and plus minus Y directions. So these are the two functions that the polarizer assembly carries out. And in itself, the polarizer assembly consists of multiple components, including glass wedges, half-wave plates, Wallerstein prisms, polarization beam splitters, and mirrors. Due to lack of time, I have not included the detailed assembly of detailed design of the polarizer assembly. But if there's a question on that, I have supplementary slide on that, and I can talk about that. But yeah, that's what the polarizer assembly does. It acts as a beam splitter and the beam steerer for the whole instrument. And then once this polarizer assembly has segregated the four channels, each channel has its own camera, which is again a set of optics, which images the complete field on a 4K by 4K detector. And this table here captures the key parameters regarding the optical design. As mentioned before, the filter is R, and the whole instrument has been designed and optimized to work in this filter. And the pupilla is of 65 mm diameter, and it's a critical number because this dictates the size of the Wallerstein prisms, which is a major limiting factor in creating the design of the instrument. And the detector is a 4K by 4K detector with 15 micron pixel size. And each pixel covers a sky of 0.5 arc seconds. And the key message that I want to give to you through this slide is that we have met all the technical design goals for the optical design. In fact, while the design goal was 30 by 30 arc minutes, with the optical design of Wallop South, we have been able to achieve 35 by 35 arc minutes field of view, which gives us around 35 to 40% more sky coverage on sky, which will help improve the efficiency of the whole survey. Now I have a slide on the problem of spectral dispersion I talked about. So the split angle for the Wallerstein prisms used in Wallop is 11.6 degrees at 600 nanometer, which is roughly the wavelength for HDSS-R filter. And the birefringence of calcite, and hence the split angle is a function of the wavelength. And even within a broadband filter like R, it causes a large dispersion. And for Wallop fluorescent prism, the dispersion corresponds to roughly around 80, spectral dispersion of 80. So, I mean, this is great if we want a spectral polarimeter, but we want an imaging polarimeter. So we had to correct for these dispersions in the um, post-polarizer optics. So to correct that, we place glass prisms at the beginning of each camera. There are two glass prisms, and these are able to correct for the spectral dispersion for within the HDSSR band for the entire field of view, and we get good PSF. Just to illustrate the problem of spectral dispersion, the image here on the right is a image from a 2-channel polarimeter on the 10-meter SALT telescope. It consists of calcite fluorescent prisms. As you can see, one is the top image is a O-beam image, and the bottom one is E-beam image. And for each star, there's one image on the top and one image at the bottom. And the dispersion is also in the opposite sense. I mean, if one goes towards the top, while the other dispersion is along towards bottom. So it's difficult to correct for these dispersions using a single glass prism, for example, after the polarizer. And unless we correct for this, we cannot do broadband polarimetry. And coming to optical performance of the instrument, through our analysis in Zemax, taking into account all the optical, mechanical, as well as thermal tolerances, we expect to achieve within 1.5 times to 2 times the seeing limited PSF for the entire field of view. The 3 images here shows the PSF at different points in the field of view. The leftmost is at the center of the field of view. The rightmost is at the extreme field of view, extreme diagonal field of view, and one in the middle is somewhere in the middle. As you can see, there's no dispersion or spectra-like feature in these images, and we get more or less Gaussian-like features, and it's very narrow PSF. Now I'll come to the optomechanical design of the instrument. We have briefly presented the optomechanical design of the instrument in a SPI proceedings paper, which you can find using the reference I have shown you. So what are the requirements for the optomechanical design? Through the analysis, tolerance analysis in Zemax software, we arrived at what are the alignment tolerances we have, and it comes out to be between 30 to 100 microns for different optical elements. So whatever the optomechanical design is, it should be able to align and hold the optics, all the optics within 30 to 100 microns accuracy. And this alignment has to be maintained at different orientations of the telescope. And there's also the effect of thermal stresses. And even if temperature changes, this alignment should be maintained. And additionally, the optics holders, the holders for the lenses and the prisms, should exert minimal stresses on the glasses. And that is important so that we don't have stress birefringence introduced in the optical beam path. Additionally, there was a mass limit of 200 kgs because of the telescope itself. And the instrument also requires multiple control motions for the various subsystems. For example, there's a filter wheel, there's a calibration polarizer system, there's a rotating half-wave plate system, as well as DVAR focusing system. So all that has to be incorporated in the optomechanical design. Now I'm going to show you 2 images of the optomechanical design. The one on the left is the core optomechanical design. The instrument begins from the top, and there's an instrument window to seal the instrument from the rest of the environment. Then there's an autoguided camera, custom made for Wallop instruments. Then there is a calibration polarizer assembly, which I will talk about in a later slide, why we need that. And then the main instrument begins, starting with the collimator assembly. Then it passes through filter wheel and the half-wave plate systems. And then there's a polarizer assembly, which is the beam splitter, main beam splitter and polarization analyzer system of the instrument. And then from that comes out 4 cameras in 4 directions. Now, as you can see, it's a very long cylinder, and we were worried about the flexure in the instrument when it is orienting at, let's say, air mass of 1 or 2. So we were worried about a cantilever effect due to telescope pointings. So based on simulations, FES simulations, we then arrived at a external truss structure, as shown in the figure on the right, which is the basic outer frame inside which this core optomechanical system is packed in. So the overall instrument optomechanical design looks like the one on the right. The main instrument is basically mounted inside a truss frame to control the flexure. And lastly, I will talk about the polarimetric calibration for the Wallop instruments. So a lot of this has already been talked about by Andre in his previous talk, so it will be helpful for others to it will be easier for others to follow these talks, follow these slides. So in Wallop polarimeter, depending on the field of view, depending on the field point in the field of view, the measured linear Stokes parameters, we call them QM and UM, can differ from the intrinsic Q and U of the source. By intrinsic, I mean on-sky Q and U of the source, without any instrumental effects. And in general, the difference between the measured Stokes parameters, QM and UM, and the actual or intrinsic Q and U parameter depend on two main effects. One is the crosstalk between the Q and U, which is basically the leaking of Q value into U value and vice versa. And second is the instrumental 0 point. Now, most narrow field of view polarimeters, for example, Robopol, have only instrumental 0 offset, which can be corrected by observing zero polarization standards. In case of Wallop, we find that there is a significant crosstalk between the QU parameters, and it changes as a function of field point. And we know that the main source of crosstalk is because of the half-wave plate in the Wollaston prism assembly. So the half-wave plate acts as a λ/2 plate only for normal incidence. For oblique angles of incidence, the retardance is not λ/2, but some other value, and that introduces crosstalk between Q and U values. So to correct for these effects and obtain the 0.1% accuracy that we aim for on sky for Wallop, we have developed a dedicated model on how to calibrate the system when we are on sky. So basically,
7 minutes.
Yes, thank you. So the idea is that we will place a calibration linear polarizer at the beginning of the instrument, and this will be on a rotation stage. So by placing it at different orientation, will give as input known states of polarization to the instrument. And from that, we will find what is the instrument measured polarization values, like what is the QM and UM. And based on what is the input and what the system what our instrument measures, we'll create a mapping function between these two values, these two sets of values. A mapping function between the instrument measured and the real polarization values. And in addition to using this calibration polarizer, we will also use standard polarized and unpolarized stars as part of building the model, and as well as testing the accuracy of the model. So to test this method, we, in the absence of a real instrument that we have not yet commissioned on sky, so we didn't wait for that. So we tested this model, this scheme, using the Zemax optical model, using the various polarization analysis features in Zemax. And we have been able to achieve better than 0.1% accuracy for the entire field of view. And to get an idea of how things work in real life as well, we created a prototype Wallop system in lab. And there also we have been able to achieve 0.1% accuracy in the calibration for the system. Now I'll come to the last few slides. Current status of the instruments. So currently, Wallop South is scheduled for commissioning in the later part of 2021. And once that happens, we are planning to commission Wallop North within 3 to 6 months. Yeah. And this is my final slide. So the main conclusions are that we have developed a complete optical, optomechanical, as well as calibration model for the Wallop instruments, which meets all its technical goals. And we are scheduled for commissioning in 2021 for the Wallop South instrument, after which Wallop North will follow. And the three papers that I have been referring to in these talks are mentioned here, so which capture what I've said in little more detail. So you can look up there if you want. Yeah, thank you. That's my talk. I'll be happy to take questions.